Hello everyone. The topic that I am going to discuss before you is about molecular geometry using VSEPR theory. What is VSEPR theory? VSEPR stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. So before we discuss about VSEPR theory, what is molecular geometry? Molecular geometry deals about the shapes of molecules. We can predict the shapes of any molecules by using what is called VSEPR theory. So according to VSEPR theory or the valence shell electron pair repulsion theory, the geometry of a molecule depends upon the number of electron pairs around the central atom. So the electron pairs are having what is called a negative charge. As a result, electron pairs will try to stay as far apart as possible to acquire stability or to minimize repulsion. So repulsive forces sharply decreases with the increasing bond angle between the electron pairs. So according to this particular theory, there are three types of repulsive interactions can be possible in a molecule. That is lone pair repulsion, that is greater than lone pair bond pair repulsion, that is greater than bond pair repulsion. That means the most strong repulsion is between lone pair and lone pair. The least repulsion is between bond pairs and bond pairs. So according to this theory, we can categorize molecules into two classes in such a way that the first category is molecules in which the central atom has only bond pairs, only what is called bond pairs, and the second category is molecules in which the central atom has both bond pairs and lone pairs. So let me go to the first category, that means the molecules in which the central atom has only bond pairs. For example, let me take one example, that is, for example, beryllium chloride molecule. So what is the question is? So our question is, what is the shape or the geometry of beryllium chloride molecule? In order to find out the geometry of any molecules using VSEPR theory, the first step is we have to draw the Lewis structure. We have to draw what is called the Lewis structure of the molecule. So in order to draw the Lewis structure of the molecule, there are certain rules are there. According to the first step, first of all, we have to write the skeletal structure of the compound using chemical symbols next to one another. For example, in the case of beryllium chloride, so beryllium atom is the central atom, this is chlorine atom, and this one is another chlorine atom. Second step is we need to count the total number of valence electrons present. In the case of beryllium, we know that it has only 2 valence electrons. In the case of chlorine, we have 7 valence electrons each. So total number of valence electrons present is, see, in the case of beryllium, we have 2 valence electrons. In the case of chlorine, we have 2 times 7 valence electrons. So total number of valence electrons total is equal to 7 times 2, 14, 14 plus 2, total 16 valence electrons we have to account in this particular molecule. So the third step is we have to draw a single covalent bond between the central atom and the surrounding atom. Then complete the octet of the atoms bonded to the central atom. That means we can complete the octet of the atoms bonded to the central atom. So when we have done this, out of the 16 valence electrons, how many electrons we used? Here we can see 6 electrons, 6 plus 6 is 12, 12 plus 2 14, 14 plus 2 16. So total 16 valence electrons, whatever was available we have used. So this is the Lewis structure of this particular molecule. What is the name of the molecule? Beryllium chloride. See, in this beryllium chloride molecule, we can see that the central atom has only bond pairs. There are no lone pairs around the central atom. So as a result, what will be the possible geometry of this molecule? This molecule will be having what is called a linear geometry. This molecule will be having linear geometry. That means here we have this is the central atom, these two are the surrounding atoms. These two beryllium chloride molecule, it cannot have what is called bendy geometry like this, because both the bond pairs are having what is called negative charge. So the bond pairs will try to stay. Assume that this is one bond pair, assume that this is another bond pair. It cannot stay like this. So it will try to stay as far apart as possible. As a result, the geometry of this molecule will be linear geometry with bond angle 180 degree. Okay, 180 degree. See, the second category is molecules in which the central atom has both bond pairs and lone pairs. Let me take one example of what is called water molecule. In the case of water molecule, we know that the central atom is the oxygen atom. Okay, so first we have to draw what is called the Lewis structure of the molecule. How to draw the Lewis structure? As I told you, there are some guidelines are there. First of all, we have to draw the skeletal structure of the compound. See, the second step is we have to count the total number of valence electrons present. What's the third step? The third step is we have to draw a single covalent bond between the central atom and the surrounding atoms and complete the octet of the atoms bonded to the central atom like this. And if in case if any electrons are left over, that we must show over the central atom. Okay. And the fourth step is if the octet rule is not satisfied for the central atom, we have to try adding double bonds or triple bonds between the central atom and surrounding atom. Okay, is it clear? Okay, next, see, when we go to H2O molecule, as I told you, this is a central atom and there are two surrounding atoms. This is one hydrogen, this is another hydrogen, this is a skeletal structure. Okay, so what I am going to do now is we are going to draw what is called the Lewis structure of the molecule. As I told you before, in order to predict the geometry of any molecule by using what is called VSEPR theory, first step is we have to draw the Lewis structure of the molecule. So what is the Lewis structure of a water molecule? See, in the case of oxygen, as you know, how many valence electrons are there in oxygen? Oxygen has 6 valence electrons. In hydrogen, we know that only 1 valence electron. So in the case of hydrogen, 2 times 1, that is equal to 2. So here we have 6 valence electrons. So total 8 valence electrons we have to account in this particular molecule. So what is next? Draw a single covalent bond like this. After drawing single covalent bond, out of the 8 valence electrons, how many electrons we use? One chemical bond means a pair of electron. This is another pair. So 2 plus 2, 4. Another 4 are remaining. 4 remaining means there is 2 pairs are there. That means there are 2 lone pairs are there on the oxygen atom. Here in this particular example, you can see how many types of repulsive forces are there. Here there is one lone pair, there is another lone pair. So obviously there is lone pair repulsion is there. Not only that, there is lone pair bond pair repulsion will be there. Lone pair bond pair repulsion, as well as there is bond pair repulsion is also there. So as a result, it is found that the 2 lone pairs, it will try to stay as far apart as possible. Okay, so what will happen? The water molecule, it cannot have this particular geometry because the